A sodium-sulfur battery is a type of molten salt battery constructed from liquid sodium and sulfur. This type of battery has a high energy density, high efficiency of charge, discharge and long cycle life, and is fabricated from inexpensive materials. However, because of the operating temperatures of 300 to 350 degrees Celsius and the highly corrosive nature of the sodium polysulfides, such cells are primarily suitable for large-scale non-mobile applications such as grid energy storage. Construction. Typical batteries have a solid electrolyte membrane between the anode and cathode, compared with liquid metal batteries where the anode, the cathode, and also the membrane are liquids. The cell is usually made in a tall cylindrical configuration. The entire cell is enclosed by a steel casing that is protected, usually by chromium and molybdenum, from being corroded on the inside. This outside container serves as the positive electrode, while the liquid sodium serves as the negative electrode. The container is sealed at the top with an airtight alumina lid. An essential part of the cell is the presence of a base membrane, which selectively conducts Na+. The cell becomes more economical with increasing size. In commercial applications, the cells are arranged in blocks for better heat conservation and are encased in a vacuum-insulated box. Operation. During the discharge phase, molten elemental sodium at the core serves as the anode, meaning that the Na donates electrons to the external circuit. The sodium is separated by a beta-alumina solid electrolyte cylinder from the container of molten sulfur, which is fabricated from an inert metal serving as the cathode. The sulfur is absorbed in a carbon sponge. Base is a good conductor of sodium ions, but a poor conductor of electrons, and thus avoids self-discharge. When sodium gives off an electron, the Na+ ion migrates to the sulfur container. The electron drives an electric current through the molten sodium to the contact, through the electrical load and back to the sulfur container. Here, another electron reacts with sulfur to form Sn2-, sodium polysulfide. The discharge process can be represented as follows. 2 Na plus 4s Na 2s4. As the cell discharges, the sodium level drops. During the charging phase, the reverse process takes place. Once running, the heat produced by charging and discharging cycles is sufficient to maintain operating temperatures and usually no external source is required. Safety. Pure sodium presents a hazard, because it spontaneously burns in contact with air and moisture. Thus the system must be protected from water and oxidizing atmospheres. 2011 Tsukuba plant fire incident. On September 21, 2011, NGK manufactured NAS batteries for storing electricity installed at the Tsukuba, Japan, plant caught fire. Following the incident, NGK temporarily suspended production of NAS batteries. Development. United States Ford Motor Company pioneered the battery in the 1960s to power early model electric cars. As of 2009, update, a lower temperature version is being developed in Utah by Ceramitech. They use a new NaSiCon membrane to allow operation at 90 degrees Celsius with all components remaining solid. In 2014, researchers identified a liquid sodium-cesium alloy that operates at 150 degrees Celsius and produced 420 mAh per gram. The new material was still able to fully coat, or wet, the electrolyte. After 100 charge-discharge cycles, the test battery maintained about 97% of its initial storage capacity. The lower operating temperature allowed the use of a less expensive polymer external casing instead of steel, offsetting some of the increased cost associated with using cesium. Japan. The NAS battery was one of the 4 battery types selected as candidates for intensive research by MIT as part of the Moonlight Project in 1980. This project sought to develop a durable utility power storage device meeting the criteria shown below in a 10-year project. 1000 kilowatts class. 8-hour charge, 8-hour discharge at rated load, efficiency of 70% or better, lifetime of 1,500 cycles or better. The other three types of batteries were improved lead-acid, redox flow, and zinc bromide batteries. The consortium formed by TEPCO and NGK declared their interest in researching the NAS battery in 1983, and have become the primary drivers behind the development of this type ever since. TEPCO chose the NAS battery because all its component elements can be abundantly found in Japan. The first large-scale prototype field testing took place at TEPCO's Tsunashima substation between 1993 and 1996, using 3x2 MW, 6.6 kV battery banks. Based on the findings from this trial, improved battery modules were developed and were made commercially available in 2000. The performance of the commercial NAS battery bank is as follows. Capacity 25 to 250 kilowatts per bank. Efficiency of 87%. Lifetime of 2,500 cycles at 100% depth of discharge, or 4,500 cycles at 80% DOD. As of 2008, sodium-sulfur batteries are only manufactured by one group, the NGK TEPCO Consortium, which is producing 90 megawatts of storage capacity each year. There is currently a demonstration project using NGK Insulator's NAS battery at Japan Wind Development CO's Mura Wind Park in Japan. Japan Wind Development has opened a 51 megawatts wind farm that incorporates a 34 megawatts sodium-sulfur battery system at Futamata in Aomori Prefecture in May 2008. As of 2007, 165 megawatts of capacity were installed in Japan, and NGK has announced in 2008 a plan to expand its NAS factory output from 90 megawatts a year to 150 megawatts a year. Xcel Energy has announced that it will be testing a wind farm energy storage battery based on 2050 kilowatts sodium-sulfur batteries from NGK Insulators Limited of Japan. The 80-ton, 2 semi-trailer-sized battery is expected to have 7.2 megawatt-hours of capacity at a charge and discharge rate of 1 megawatt. In March 2011, Sumitomo Electric Industries and Kyoto University announced that they had developed a low-temperature molten sodium-ion battery that can output power at under 100 degrees Celsius. The batteries have double the energy density of Li-ion and considerably lower cost. Sumitomo Electric Industry CEO Masayoshi Matsumoto indicated that the company aims to begin production in 2015. Initial applications are envisaged to be buildings and buses. Challenges. Corrosion of the insulators was found to be a problem in the harsh chemical environment as they gradually became conductive and the self-discharge rate increased. Dendritic sodium growth can also be a problem. Applications. Electricity storage for grid support. As noted above, NAS batteries can be deployed to support the electric grid. In 2010, Presidio, Texas, built the world's largest sodium-sulfur battery, which can provide 4 megawatts of power for up to 8 hours when the city's lone line to the Texas power grid goes down. Under some market conditions, NAS batteries provide value via energy arbitrage and voltage regulation. NAS batteries are a possible energy storage technology to support renewable energy generation, specifically wind farms and solar generation plants. In the case of a wind farm, the battery would store energy during times of high wind but low power demand. This stored energy could then be discharged from the batteries during peak load periods. In addition to this power shifting, it is likely that sodium-sulfur batteries could be used throughout the day to assist in stabilizing the power output of the wind farm during wind fluctuations. These types of batteries present an option for energy storage in locations where other storage options are not feasible. For example, pumped storage hydroelectricity facilities require significant space and water resources. While compressed air energy storage requires some type of geologic feature such as a salt cave, NGK Insulators Limited develops sodium-sulfur batteries as grid storage in Japan, France and the United States. Space applications. Because of its high energy density, the NAS battery has been proposed for space applications. Sodium-sulfur cells can be made space-qualified. In fact, a test sodium-sulfur cell was flown on the Space Shuttle. The sodium-sulfur flight experiment demonstrated a battery with a specific energy of 150 watt-hours per kilogram, operating at 350 degrees Celsius. It was launched on the STS-87 mission in November 1997, and demonstrated 10 days of experiment operation in orbit. Transport and heavy machinery. The first large-scale use of sodium-sulfur batteries was in the Ford EcoStar demonstration vehicle, an electric vehicle prototype in 1991. The high temperature of sodium-sulfur batteries presented some difficulties for electric vehicle use. However, the EcoStar never went into production.